Hello and welcome to Toddcast number 12. Want to pick up where we left off last one in terms of acid base chemistry. And so this time, going to focus primarily on identifying common acids, common bases, their pKas, a little bit of number memorization, and then looking at equilibrium just like we finished the last lecture with. So the common pK values and consequently pKb values, because 14 minus pK is pKb. Compounds you have to know. For OChem, I might have briefly mentioned the 5, 10, 15, 20, 25 rule. I'm just going to make it today the 5, 10, 15 rule. But there are certain compounds that are acidic that you see over and over in OChem. And one of them is a carboxylic acid. So this R just stands for anything from H, CH3, CH2, CH3, whatever alkyl group, with something irrelevant to the functional group, something that's just an R dangling off. pK will be anywhere from 3 to 5, depending on how electron donating or withdrawing the substituents on this R group happen to be. But I'm going to focus on this one is 5. So there's a few that are 10, so I'm going to memorize that as being 5. The amines, they're actually a little closer to 9 than they are 11. So I'm going to put these as 10, but with a little minus because it's a little bit less. Phenols are right on 10. Now you can put substituents on this ring to add electron density or withdraw electron density, make the pK go up a little, down a little. But a phenol, OH on a benzene ring, usually is around 10. And then thiols. Thiols end up being 10 plus a little bit, depending on, again, what the R group does. So 5, 10, but amines slightly less, phenols right on, thiols a little bit more. And then finally, alcohols. Alcohols are around 15. So your 5, 10, 15 rule. Things are basically multiples of 5. So if you know acids are 5-ish, a little bit lower as well, alcohols are 15-ish, a little bit higher as well, and you know the other ones are in 10 range, you can make a lot of pK predictions. Okay. So we know carboxylic acids are around 3 to 5. Notice, though, I added AA here. So I want to add one extra piece of information. This is more leading towards biochem for those who go in that direction. But this stands for amino acid. An amino acid has an amine and an acid. When it's on an amino acid, the carboxylic acid, because of the inductive effect, which we'll learn about from the amine group, makes it a little more acidic. So instead of being 3 to 5, it actually is somewhere between 2 and 3. And its conjugate then, the conjugate acid, if this is 3 to 5, 14 minus 3 is 11, 14 minus 5 is 9, so pKb is 9 to 11 for when it's deprotonated. And then 2 to 3, 14 minus 2 is 12, 14 minus 3 is 11, so 11 to 12 for the pKb for the carboxylate, or deprotonated carbonyl group, or carbonyl terminal. We mentioned last time the pH will dictate which charge it is, because 7.4 physiological pH is higher than 2, 3, and 5. pH is higher. When pH is high, it feels basic. When it's basic, it'll be deprotonated. So typically in our body, we see things as carboxylates. So we don't really worry about lactic acid. It's actually lactate that'll build up. We don't worry about succinic acid. It's succinate. Don't worry about glutamic acid. It's glutamate, and so forth. So we worry about the deprotonated form biologically. There's also the amine group. So the amino terminal is around 9 to 10. In amino acids, around 9 to 11 is just a straight amine. When I do 14 minus 9, I get 5. 14 minus 10, I get 4. 14 minus 9, I get 5. 14 minus 11, I get 3. So this is pretty straightforward. Now the physio form in this case, 7.4 is less than these. So it'll feel acidic. When it's acidic, it'll be in its so-called protonated form. Okay. So last on the agenda then, want to toss 2 compounds. We won't really see much of them in OChem. They're going to be strictly physiology or bio, but you know that carbonic acid buffers the blood. And so it's pK1. It has 2 protons, so pK1, the first one to come off, around 6.4. 7.4 is higher, so it exists as bicarbonate in the blood. And then phosphate, inorganic phosphate in the body, 7.2 for the pK. So 7.2 is really close to 7.4. So 7.4 is only slightly higher. So I'll get just a little more of this. So it might be 60% the 2 minus and 40% of the 1 minus. It also makes note then that the DNA backbone is negatively charged for the same reason. Phosphates, when you find in the body, are typically -1, possibly -2 in some cases. Okay, so we have all this straight memorization. So now I want to apply it. I want to combine what we did last time, and that was look at the stability or strength of acids. So again, two ways I can do this. I know the pK of the carboxylic acid is roughly 5. Thiols are just a little bit more than 10. So I can do one of two things. I can do product pK minus reactant pK, 10 for the thiol, minus 5. 10 minus 5 is 5, so 10 to the 5th. 10 to the 5th is greater than 1. This reaction will favor the forward direction. Or I can say lower pK for the carboxylic acid makes it stronger. Higher pK for the thiol makes it weaker. So stronger acid, weaker acid, reactions always go to form the weaker compound, because weaker means less reactive means more stable is where it wants to go. So stronger acid, weaker acid has a stronger conjugate base on the opposite side, stronger acid has a weaker conjugate base on the product side. Reactions go from stronger to weaker because more reactive, less stable, less reactive, more stable. So reaction goes that way. K equilibrium greater than 1, but as mentioned, it's going to be around 10 to, in this case, I'm going to say the 6th, because 11 minus 5 equals 6. So this one we're going to do a little bit faster. This is an alcohol. I know this is 15-ish. This is a protonated mean. This is 10-ish, a little less than 10, so maybe around 9. This might be a little higher than 15, but we'll say 15 ballpark, 16 ballpark. This one is 9 to 10, so I'll say 10 just for simplicity. 10 minus 16 is minus 6. 10 minus 6 means unfavorable. Also, this is a weaker acid because it has a higher pK. This is the stronger acid. So stronger acid would go with a weaker conjugate base. Weaker acid goes to stronger conjugate base. Stronger are less stable and more reactive, less stable. The weaker ones are less reactive, more stable. So it's going to go backwards. And again, looking at around 10 to the minus 6. So one more of these because I have a little more room left. An alcohol again, or is this a phenol? And this is what's hard from the structure. So RCH2 with an OH looks very much like an alcohol. 6H5 is that benzene ring. So just to revisit, if you have double bonds everywhere, and you have an H on a carbon, 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 and therefore OH. So I have C1, 2, 3, 4, 5, 6, H1, 2, 3, 4, 5. So that's actually phenol. Phenol has a pK of roughly 10. Thiols are a little more than 10. We called it 11 up here. So I'll go with that. I don't know if it's perfect, but close enough. So 11 and 10, product minus reactant. 11 minus 10 is 1. 10 to the 1 means this will have a K equilibrium of around 10. So it favors it by about a 75 to 25% ratio. So stronger acid have a weaker conjugate base, weaker acid, stronger conjugate base. Stronger are more reactive, less stable, weaker, less reactive, more stable. So we go through the same routine. Once we move to the weaker reagent, equilibrium greater than 1 based on this arrow. Specifically, it's around 10 to the 1. Okay, so now let's apply it like a question. So I've beaten those pretty thoroughly. So this time I'm messing with you. Instead of writing the structure out, I'm going to go with nomenclature. Alcohols, an R with an OH. We know pK is 15-ish. A carboxylate is the conjugate base of a carboxylic acid, which means if this is carboxylate, then a carboxylic acid is on the other side. Alcohol, when deprotonates an alkoxide, but this is around pK 15, 16, 17, somewhere in that range. So we'll say 15 just to toss a number out there. Carboxylic acid is around 5. 5 minus 15 would mean 10 to the minus 10. 10 to the minus 10 is highly unfavorable. So it's going to say as a carboxylate and alcohol, it doesn't want to go in the forward direction. So an alkoxy and a carboxylic acid. So just to draw this ROH, C with an O minus and an R. Alkoxide is RO minus, and carboxylic acid is RC1O with an OH. So this proton here has been transferred to here. So again, this is a pK around 15-ish. This is around 5-ish. 5 minus 15, 10 to that power equals 10 to the minus 10. Highly unfavorable. Okay, let me erase my writing and toss in the numbers we're looking at. So 16 and 5 I went with. 5 minus 16 is 10 to the minus 11, highly unfavorable. Weaker acid on that side, stronger acid over there. We go from the side of stronger acid to weaker acid. So K equilibrium less than 1, and specifically K equilibrium is approximately equal to 10 to the minus 11, highly unfavorable. Thiol and phenoxy. So phenoxide. So RSH, which is around 11. Phenoxide is a phenol that's been deprotonated. Let me be a little more specific with my bonds. That means over here we're going to get an RS minus, and we're going to get the phenol. Phenol, I know, has a pKa of around 10. So stronger, weaker. Reactions go in the direction of the weaker, so I know it's going to go backwards. But it is 10 to the 10 minus 11, which equals 10 to the minus 1, which means it's barely going to go that way. So again, it's going to be out 75 on this side, 25 on the other. That'll work roughly to the math of 10 to the minus 1 when I plug it into a K equilibrium. Product times product over reactant times reactant has equal 1 over 10. Okay, I'm going to erase what I wrote and let the words come in. Alkyl sulfide, that's when it's deprotonated. Ide means it's negative. Phenoxide goes to phenol. pKs of 11 and 10. Weaker, stronger. Reaction goes from stronger to weaker. But this time, it's only 10 to the minus 1. So here it was 10 to the minus 11. Here it's 10 to the minus 1. So the product minus reactant approach is also very easy. So draw a favorable acid-base reaction involving ammonia and acetate. Well, dang, this just got a lot harder. So I want to have ammonia and acetate. The problem is ammonia is a weak base. Acetate is also a weak base. So I have to figure out what their conjugate acids are. So ammonia is NH3. So I got to worry about NH4 plus. And then acetate, sorry, missing C, O2 minus. So acetic acid will be the same thing, but protonated. So H3C, CO2H. Okay, and then let me move the minus to an easier to view spot. So that's my minus charge. This is my positive charge. Okay. So ammonia and ammonium, I know ammonium has a pK around 9. Acetate has a pK of around 3, 4, 5. So I'm going to go with 4 or so. And actually, if you happen to have it memorized, 4.7. So I'm in the ballpark. The point being, this is a stronger acid. So if I went favorable, I know it's got to go from stronger to weaker. If it's going to be favorable, stronger has to be on the reactant side. Products have to be weaker reagents. So this acid, this carboxylic acid, has to be on the reactant side, and the weaker acid, ammonium, has to be on the product side. Okay, so let me clear what I just wrote and go ahead and let the words flow in. So sorry to do it this way. No, it's a little, it's going to be counterproductive, but I just don't erase everything. So there's my ammonia, there's my acetate, weak base, weak base. The conjugate is NH4 plus. The conjugate of this is acetic acid. Acetic acid is a stronger acid, so I want it on the reactant side. This is my weaker acid, so I want it on the product side, which means this has to go to the reactant side. And this one has to go to product side. Perfect. Now again, 4 and 9. So for the K equilibrium equals 10 to the 5th, because 9-ish minus 4-ish, somewhere in that range, is going to be 5. Okay, so I feel pretty good about this. So now I want to shift gears into trying to decide how these are going to deviate. So not every carboxylic acid is 5, not every amine is 9. A few things can affect it. So amongst the things that can affect it are pKa. It's going to be a little more specific. So we say pKa of phenols are around 10, but truth is around 9.95, which rounds up to 10. So mentioned earlier that donating or withdrawing groups are going to impact the relative acidity. So if something donates in by resonance, so this cannot go all the way to the OH, but what it can do is it can give me a negative charge really close to the OH. A negative charge next to the OH is going to make the whole system a little less positive, and in doing so then makes it a little less acidic at H. So I'm going to trying to redraw my lone pair. So this is lone pair on this carbon right here. It's negatively charged. It's going to make this end electron rich. So this is an electron donating group because it has a lone pair. This is going to be electron rich right here, which means pK is going to go up. So 9.95 to a higher number. So there's my lone pair. Lone pair is electron donating group. It's got to be greater than 9.95. Okay, 10.24, not bad. Seems reasonable. Now I'm going to look at another one. This one now has a pi bond. Pi bonds are known as electron withdrawing group. So it has a pi bond, so pi bond electron withdrawing group. I'm going to pull electron density from there, which will pull it from there, which will steal it from here, which will ultimately steal it from the O on the phenol, leaving me with minus on that O, and therefore plus on that O. Let me redraw that plus to be a little cleaner. Now that's plotted a plus on it, it makes it electron poor. So this electron withdrawing group makes this electron poor right here, which means 9.95 is too high. It's got to go down from there. So this number has to be less than 9.95. Highest electron donating group, less than 9.95, ends up, it's in the 8 range, 8.08. So resonance can be used to predict whether something's going to be more acidic or less acidic. Electron donating groups are lone pairs being donated into the network. Electron withdrawing groups are pi bonds pulling electron density away. So lone pair donates in, makes it a little less acidic, pK goes up. This one, pi bond pulls it away, pulling it away makes it electron poor, makes it a little more acidic. Know it conceptually. Again, there's those who say the more resonance structures you can draw, the more stable it is. The more stable, the better it is at pulling away. So I could pull 1, 2, 3, 4 arrows. So in theory, I should be able to draw 4 resonance structures. Here, I only have 1, 2, 3 arrows, so it doesn't help as much. So this one, better resonance. So it pulls it from 9.95 by a greater amount, almost 2. This one goes up by just 0.3. Okay, feeling good. That is resonance. We've done resonance pretty thoroughly, but it will show up on a lot of questions and a lot of tests. Okay, last one I want to do. I'm going to clear everything at this point. I apologize, but it's just so chaotic. This group, trying to figure out what exactly it is, this first atom attached here, electron withdrawing group. But because of the lone pair here on this O, because that can donate in. This is going to donate a little bit less. So it's the same resonance as we did before, but because this is donating in as well, it doesn't accept this as much. So it's not as electron withdrawing. It's still electron withdrawing because the first atom attached to the ring is a pi bond, but it's not quite as severe. So pi bond is electron withdrawing, though it's going to be less than 9.95, but it's not as much. So it doesn't go down by as much as this one did, only by about 8.47. So what the heck is going to be tested on this? Well, memorizing exact numbers, that's a bit much, but at least knowing it's a lot greater, a lot less, or a little less is reasonable. So knowing what kind of group you have. So always look at the first atom attached. First atom attached has lone pairs. Lone pairs are donating. First atom attached is part of a pi bond with no lone pairs, withdrawing. Part of a pi bond with no lone pairs, withdrawing. Look at the first atom attached to the network, the one so-called allylic. There's my double bond. This is one away from the carbon-carbon double bond. This is double bond here. This is one away. Okay. Inductive effect. We've already been through Funkelbrich, but we're going to do it again. If you have a fluorine, it's going to withdraw a lot. If you have an oxygen or nitrogen, it's going to draw a little bit. Cl and Br a tiny bit. And by the time I get to adding a C, it's not going to pull away hardly at all. So we do this by looking again at structures that can share electron density. But in this case, instead of doing resonance through the pi system, I'm going to compare what happens when I have a substituent on here. So CH3, this substituent has no lone pair, so it can't be donating by resonance, has no pi bond, so it can't be withdrawing, so it can only do it by the inductive effect. H is slightly less electronegative than C, so H's can donate just a little bit of electron density to that carbon, which in turn can donate it across the structure, but by the time it gets all the way to this carboxylic acid, it's not going to be that strong. It's so far away, it's going to dissipate. So this will, in fact, go up a little bit because it's now less acidic because it's electron rich. But less acidic means the pKa is going to be just a hair above. So it only went up by about 0.6. Not terribly noticeable. What if it was CF3? So same story as before, only now fluorine is on the extreme end. So fluorine is highly electronegative, so fluorine is actually going to take. So I'm going to draw a much bigger arrow, which is going to end up making an electron withdrawing group. Makes that electron 4, which means it's going to go down from 5.0. But because F is so electronegative, it's going to pull it far more than H donated. So if H donating made it go up to 5.6, this one's going to go down, and certainly by more than 0.6. So it goes down to around 3.8. So it goes down over a full 1 in terms of pKa. This is known as the inductive effect. So quick little physics pit stop. If I have two spheres made of conducting material, copper is a good example. If I introduce a plus charge on the sphere on the left, a +6, let's say, the sphere on the right will start feeling it, and the negatives will move over to one side, and the positives will be repelled on the other. So this plus charge on the left induces a dipole on the right. So these plus charges pull electrons to this side, repel positives to the other side, so you get a dipole. That is called induced charge or induced polarity based on this this structure here. So we call it inductive effect because we're inducing something in OChem, but we're going to call it induction or an induced dipole in physics. If I were to increase the plus charge, then the amount that moved over would also increase. The other factor, so how big the plus charge is, the magnitude of the plus on the side is going to affect it, but so will proximity. If I move it further away, and I put the same amount of plus charges on there, it might only pull over 3 charges because the distance, it dissipates with distance. So magnitude and proximity both impact how much it's going to induce this polarity into a conducting sphere. Okay, so we'll look at that. Here we have that baseline we want to compare to. This is acetic acid, carboxylic acid group, and a CH3, drawn it in the, being a little bit specific about stereo, about in and out. If I replace the three H's with three F's, F's we know are electron withdrawing, and there's three of them, and they're very close, which means this is a really impactful scenario. A very large inductive effect because it's so positive, or it's going to be so positive because this is going to pull so much density and because it's close. So it ends up, it drops severely all the way down to about 0.2. If I were to use chlorines instead, not as electronegative, they're still very close, but because they're not as electronegative, they're not going to pull as much. So it's got to be higher than 0.23, but less than 4.74. Ends up 0.6-ish, 0.7-ish, around there. Okay, so what if I have Cls, but instead of having them one carbon away, what if I make them 2 carbons away? So we learned from physics that the further away the charged site, in this case, the electron withdrawing electronegative chlorines, the less the impact. So if this is 0.66, it's got to be higher than 0.66 because it's not pulling away as much, but certainly less than 4.74. And then the other impact we want to look at, 3 chlorines lower it all the way down to 0.66, but if it's just 1 chlorine, just as close as this one is, but these 2 Cls aren't there, we have H's, it's going to pull away, but again, not as much as this, so less than 4.74, but cannot be way down there, so you're probably looking at 2 point something again. The last one is going to look at 2 chlorines, and I could have left it here and put like one here and here, the here and here, because this can rotate around, doesn't really matter, it's the same thing. But 3 made it 0.66, 1 made it 2.86, so I know it's got to be somewhere in between there. So I'm guessing 1 point something, 1.4-ish maybe, 1.35. Okay, so I feel pretty good about this concept, and I'm going to keep in mind the strength. F is more electronegative than Cl. 3 is more than 2, 2 is more than 1, and then proximity. Close, it has a big impact. Further away, it has less impact. Okay, that is a so-called inductive effect. It simply depends on relative electronegativity of the atoms attached to the molecule that are not the group we're staring at. Okay. So onward we go. Introduction to mechanisms. So want to justify why we're spending so much time doing acid-base chemistry, because this isn't acid-based chemistry, this is supposedly organic chemistry. So with that in mind, introduction to mechanisms, we're going to move arrows in the same way we did resonance. We're going to move them in the same way that we did acid reactions. So we want to look carefully at an acid reaction, a proton transfer reaction, and compare how the electrons flow to a typical organic reaction. That said, we're going to always say negative finds positive. This is negatively going to be negatively charged because HCl is more electronegative. So if Cl is negative, H is positive. So this negative, this lone pair on nitrogen, this delta minus, is going to attack the hydrogen. When it attacks the hydrogen, it's going to literally steal it and push the electron density over to chlorine. Meaning, I will now have the following. I'll have H3N like I had before, but now it's bonded to an H and it carries a positive charge. And I will have Cl with the original 3 lone pairs and a 4th lone pair for a negative. This is arrow pitching. So left arrow shows a lone pair moving to an atom to become a covalent bond, check. And the covalent bond breaking to become a lone pair on an atom. So when a lone pair goes to an atom, it becomes a bond. When a bond goes to an atom, it becomes a lone pair. Sounding an awful lot like resonance. Electrons go in to form a bond breaks to form electrons. Very, very similar. Okay, so I'm going to erase what I drew so the picture is a little prettier. So NH3, check. Lone pair is now a bond, check. H is there, check. This bond is now a lone pair. I have my original 1, 2, 3. I now have the new one from that bond breaking, and I now have the minus and the plus. Okay, that's called a proton transfer reaction. I'm going to look at the more complicated one now. Here's my negative. Negative is going to find positive. The positive is the H. So this is looking so much like resonance that I'm grateful we did all that resonance, because now I understand this a little bit better. So that's like that. This O is now bonded there. This O up here has negative. All the atoms remain the same, but now the H, the proton, has been transferred from this, the O that's on, to this carbon that's picking it up. Okay, so again, what has happened exactly? So I'm going to erase everything I've written and say I'm going to focus on this is going to go here, this is going to go here. So I could have pushed it in like I did. Emphasize I can also, lone pair becomes a bond becomes a lone pair. I did the way I drew it before. Lone pair became bond went to bond, and then bond became a lone pair. I did it differently. Have a slight issue on this picture. So I know why I did that, because I was jumping ahead of myself. But the left arrow shows a lone pair moving to become an atom, just like before, or move to an atom to become a bond, right? Sorry. And then the bond breaking to become a lone pair. So notice these are very similar, the two stories and the two outcomes. So far, so good. I think I like this. Okay. So introduction to mechanisms. We're going to take that same proton transfer reaction we just did. We're going to look at what's called a mechanism. So now, instead of a lone pair picking off an H like we did before, a lone pair has to find a carbon. So this carbon right here has what's known as a delta plus. That makes it a target of this negative. So this is a Lewis base that, instead of pulling off a proton, is now going to attack at that carbon. This carbon with a delta plus. So the question is, what happens first? Does this go in and push that out, or does this leave to make room for it? So as it is, this case, this actually leaves, and in doing so, leaves a plus charge there. Notice the C3 is free to move over, because when it moves over, it's a carbocation with a empty p orbital. So just a reminder of what we were doing all last chapter. This empty p orbital right there, it can be attacked by this sulfur. Sulfur could attack from the right or could attack from the left. So I'm going to get rid of my p orbital just to show that it's attacking this carbon. So bond becomes a lone pair becomes a bond. There's no longer restriction of being a pi bond, we'll note. So now it was a sigma bond, because this is an actual chemical reaction, not a resonance structure. So a bond breaks, becomes a carbocation, and then this nucleophile attacks. The plus charge on sulfur, don't want it, so I have a negative chlorine over here, and I have this positive charge here, so chlorine can come in and take the H. That's going to be my final step. The H goes off. I'm just showing the H coming off, and the Cl minus can pick it up, and I'm left with this neutral molecule. So sigma electrons become a lone pair, not a pi bond, but a sigma bond. Lone pair becomes a sigma bond, and then sigma electrons become a lone pair again, and then another lone pair from chlorine is going to pick up the H. So those will become a Cl to H bond. So far, so good. I think I like this. Another reaction we're going to learn, so this is substitution. We have substituted a sulfur, alkyl sulfur group for a chlorine. So chlorine is out, sulfur group is in. Elimination, we eliminate two things and we end up with a double bond. So elimination is going to work in the following way. I'm going to first make a lone pair become a sigma bond. So now this becomes OH2 with a plus charge, because it picked up a plus, so it keeps a plus. Water is highly stable, So if I have this pi bond leave, or sigma bond, I'm so sorry, sigma bond will leave. I'm going to be happy because I generated water. So a lone pair became a sigma bond became a lone pair. This plus charge is now formed. This H didn't magically appear. It was here the whole time. We had 3 bonds, so fourth H, 3 bonds, so fourth H. So now I'm just drawing it, and it didn't matter if I drew it in front or back. I could have drawn it differently, but I don't know, just creature habit. I draw the lower one in front, the upper one in back, just for no other reason than to draw it that way. But now we can take these electrons and move them over. So let's see. Lone pair became a pi, or sigma bond, sigma became a lone pair. Now we're going to have bonding electrons become bonding electrons. So, and the sigma becomes a new sigma bond. So sigma bond to sigma bond. So kind of a rare thing, but all the electron movement we're doing is pretty much exactly what we've been doing with resonance and proton transfer. So moving electrons within a molecule through resonance, moving electrons in a proton transfer reaction like we did just before this, gives us the guideline to how we're going to draw these mechanisms, how we're going to keep track of things. So a mechanism is a step-by-step account during an organic chemistry reaction of how it goes from where it started to where it finishes, and we emphasize the intermediates it forms along the way. So how it goes from where we start to where we finish, going through various intermediates. But the key thing is to note this is very, very much like the way we draw resonance. Electrons, lone pairs, become like bonds become lone pairs become bonds. So same thing we did with resonance, but now it can be sigma because we're actually breaking bonds. Okay, so air-pitching rules, things you have to know. The electrons are moving because they're lightweight, easy to move. Atoms are heavy, they don't move as easily. So we always move electrons from where they are to where they are not. So we move them from negative, where you have rich electron count, to positive, where you have none. So OH minus, lone pair can come in and attack this H. The electrons that were in this bond can go over here, so now I have water and Cl minus, proton transfer reaction. Double-headed arrows represent 2 electrons, single-headed represent 1. So 1 will be a free radical reaction. So here I drew 2-headed arrow, so it's getting 2 electrons. So that chlorine comes off. I'm now going to have 1, 2, 3, 4 electron pairs where it had 3 to begin with. Now it picked up a 4th of the negative charge that resulted from it. And then what's left behind is carbon in the middle with CH3, 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 and a plus charge on the central atom. Free radical chemistry, notice that these are single-headed arrows. So just one side, not both. That represents 1 electron. And if I really want to be, I probably should start these a little closer to the actual pi bond, or sigma bond, excuse me. So it's going to go from here to there, but it's only 1 electron. That's why you see 1 dot here, 1 dot here. So 2-headed arrow becomes charges, 1-headed arrow becomes free radicals. Arrows start at electrons, and they move to an atom, or they move to the middle of a bond, but they do not start at the charge. I don't draw it from the charge. I draw it from electron pair. So electron pair in the bond, electron in the bond, or I draw it from a lone pair to an atom. But I do not start at a charge. I start at a lone pair. So I started at electrons of whatever type they are, so lone pairs or bonds. Now at charges, the book got this wrong, actually, which is kind of interesting. The book has a lot of examples where they cross this up. And if they finish in an atom, it becomes a lone pair, like it does here. And if they finish between atoms, like it does here, between the O and the H, then it's a bond. So hopefully that seems okay. These are simple rules. We're going to do it so much in this class, you're going to get incredibly used to it. So this lone pair goes to this H, that goes up like this. So just basically drawing the same thing up here. Notice we did not start from this, from that negative charge. Let me emphasize that's a negative. I do not draw from the negative across. So if I drew that arrow right there, no, 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 no. That's the emphasis on that one. Okay, so last thing I want to do is want to shift into test writer mode. And everything we've done in this video specifically was determine K equilibrium for an acid-base reaction, decide which reaction is stronger or weaker based on pK knowledge or by just intuition of certain functional groups. And then we did arrow pushing. Arrow pushing is going to be the entire rest of the semester and all the way through your entire OChem career. So that will revisit many times. But for acid base, want to figure out how to ask questions. And then the last video we're going to do on this chapter will be asking these questions. But I can ask you the same question multiple ways. So the question is, which acid is stronger? So that's your fundamental question, but you can ask it multiple ways. Stronger acids have weaker conjugate bases. So instead of saying which acid is stronger, can I instead ask which one has a weaker conjugate base? Sure. I could ask it, which acid is a better proton donor? So just talk about a Lewis base definition or Bronsted-Lowry definition. Which one is this? And so Lewis is electrons. This is Bronsted-Lowry, proton donor. Which one gives off an H plus better? So which one is a better Bronsted-Lowry acid? Which acid is a better electron pair acceptor? So again, is that Bronsted-Lowry or is that Lewis? And in this case, we're talking about electron pairs, so we're talking about Lewis. Which one is a better Lewis acid? So I should make note of that. This is a Lewis acid. This is a Bronsted-Lowry acid. 5, which acid gives a higher K equilibrium when reacting with a certain base? Could be ammonia, could be whatever else. But the bigger the K equilibrium, the more it goes in the forward direction. We know it goes from stronger to weaker. So the more it goes in the forward, the conclusion, it must be stronger. Which acid has a greater Ka? Which one dissociates more? That could also be then written as which one has a lower pK. We looked at that. Which acid has a conjugate base with a lower Kb? Which conjugate has a higher pKb? We can start getting completely carried away. I'm starting to run out of room, but there's so many different ways to ask the same question that you have to study in the following way. Know which acid is stronger, be able to determine that looking at two acids, and then realize all these translate back to which is a stronger acid. So on the test, on homework, on any question you run into, be able to answer which acid is stronger, and then be able to recognize how the question is worded, what they're asking in terms of which acid is stronger, and you will do great. Okay, this is where I'm going to tie this lecture off. But again, the third one in this block, this group, this chapter, is going to be applying acid base. So with that in mind, let me go ahead and shut this down. And thank you, and I will see you at a future recording.